Okay, folks, this is going to be going over your next lab assignment for Chem 1212 lab. So this experiment is going to be relating solubility, equilibrium, and thermodynamics. And I'll be handing out this assignment to you all to return to me at a specified date. And of course, like last time, you'll want to complete the pre-lab and then the lab report using data that we're going to provide for you. Now, if you look at the pre-lab, you might notice if I scroll down here a little bit, there's only one pre-lab question, which is maybe a little bit ominous. And this kind of gets at one of the reasons why I wanted to make this video is that, at least from a mathematical perspective, this is probably the most complicated lab of the entire semester. So if you look at the pre-lab, it tells us that we're given the delta G, or the Gibbs free energy change, for a reaction at two different temperatures. So the first temperature is 15 Kelvin, the second temperature is 75 Kelvin. And we have different associated delta G values for the reaction at those two different temperatures. And it asks you to solve for delta H, the enthalpy change, and delta S, the entropy change. So let's go ahead and go over this. The equation that relates delta G, delta S, and delta H is shown on the screen now. Delta G equals delta H minus T times delta S, where delta G is your Gibbs free energy change. That's in kilojoules per mole, as you can see in the question. Delta H is the enthalpy change with the same units. T is the temperature in Kelvin. It needs to be in Kelvin. In this problem, it's already provided for you in Kelvin, but when you work with the data in the lab, you're going to need to remember that it needs to be in Kelvin, not degrees Celsius. And delta S is the entropy change, which has units of joules per mole Kelvin. Now, when you multiply the temperature and the entropy change together, the kelvins are going to cancel and you'll end up with joules per mole. So to add that to delta H, add or subtract it, you're going to need to convert that into kilojoules per mole. So you'll essentially need to divide it by 1,000 before you can plug it directly into that equation. Now, what we can do is we know different delta G values for this reaction at two different temperatures. And so you can see on screen here that we can set this up. Delta H and delta S aren't going to change. They're the same for a reaction at any given temperature. But T and delta G change. So what we have essentially is a system of two equations with two variables. So this is kind of like a high school algebra problem where delta H and delta S are the two variables that you need to solve for. So if you plug in your values for T and delta G, as shown in the following manner, then you should be able to solve for delta H and delta S. It's a little bit of algebraic manipulation, but I'm sure you all know how to do that. Okay, so this question in the pre-lab is very similar to what you're ultimately going to need to do with the data in the lab. So let's actually take a look at this laboratory procedure. Now I'm going to explain what the experiment is, even though you're not going to be conducting the experiment yourself, just so you can get a better understanding of what's going on and help you answer the questions. So if you were in lab, what we would have is some bottles with saturated calcium hydroxide solution in those, and you'd get some of that solution and split what you obtain into two separate beakers, so two separate samples of calcium hydroxide solution. We know that it's a saturated solution because there would be more calcium hydroxide present than can dissolve, so it would be an opaque solution with a bunch of white powder not completely dissolved in it. So to make sure that we're going to titrate only the saturated solution and not any of the solid, what we need to do is filter those two solutions. So you take the beaker with one portion of that solution and filter it using the apparatus that you see there on the left. And the result of that is you get a saturated calcium hydroxide solution at whatever room temperature is. Now with the second portion of that solution, what you would do, instead of just directly filtering it, is you would boil that so that the solution reaches 100 degrees Celsius. And after it boils, and while it's still at the boiling point of water essentially, you would then filter it at 100 degrees Celsius. And the result is that you get a saturated calcium hydroxide solution at 100 degrees Celsius, which is not going to contain the same concentration of calcium hydroxide as the room temperature solution. Remember, the solubility of just about all substances in water changes as a function of temperature. And without giving away too much, calcium hydroxide, even though it's a solid, kind of behaves in a slightly counterintuitive way where it actually is less soluble at higher temperatures. The vast majority of solids, especially ionic solids, are more soluble at high temperatures, but calcium hydroxide is a little bit weird. So what we're going to do with those two solutions that we filtered is we're going to titrate them. So for this, we're going to use hydrochloric acid with a known concentration. And so what you'd do is you'd measure out a known volume of the solution from step 2 first, and you titrate that with hydrochloric acid, and you know the hydrochloric acid concentration. Since calcium hydroxide contains hydroxide ions, it's a base. In fact, it's a strong base. It just doesn't have very high solubility. And so that will react with hydrochloric acid, a strong acid, in an acid-base neutralization reaction. And you'd do that twice, so you have 2 trials worth of data. Then you'd do pretty much exactly the same thing, except with the solution that you boiled and then filtered while it was hot in step 3 there. So you'd have 2 more trials there. And you know that you've reached the equivalence point in these titrations, not because you'd be monitoring this with a pH probe. You wouldn't be doing that like you would have last week. You'd just be using an indicator like phenolphthalein. Phenolphthalein is more commonly used when you're adding a base to an acid, in which case it starts off clear and then becomes pink. With this titration, we're actually taking our calcium hydroxide solution and we're adding the hydrochloric acid solution to it. So the pH starts very high at a very basic solution, and then as we add the hydrochloric acid, it decreases. So the phenolphthalein would actually go from pink to clear, which is the reverse of kind of how you see a lot of titrations conducted. All right, so to actually use those results, we need to look at a couple of chemical equations and discuss what to sort of get from our data and how to apply it. So the first equation is the equilibrium for the dissolution of calcium hydroxide in water. And like any ionic solid, this involves taking the solid reactant on the reactant side, dissociating into its constituent ions on the product side in aqueous solution. So for calcium hydroxide, that's 1 equivalent of calcium ions and 2 equivalents of hydroxide ions, as indicated in the formula there. So to kind of figure out what's going on with this equilibrium, we can put together an ice chart. Remember, solids don't really participate in equilibrium, so we can ignore that first column. And initially, if we start with pure water and we add calcium hydroxide to it, there's not going to be any calcium ions initially, and there's going to be next to no hydroxide ions. Of course, as you know by now, water autoionizes, and so if we have distilled water, there'd be a 1 times 10 to the minus 7 concentration of hydroxide ions initially, but that is so much smaller than the amount that we're going to add from the calcium hydroxide that we can basically just treat that initially as 0. Now we know that whenever calcium hydroxide dissolves, twice as much hydroxide ions go into solution for every 1 calcium ion, and you can tell that from the coefficients in our balanced equation. So the change portion for calcium is just going to be plus x, but for hydroxide it's going to be plus 2x because it's going to have to be exactly twice the amount. Now I'm not going to fill out the rest of the chart, you can kind of do that on your own, but you can see, you can use that chart and you see the expression for KSP, which is also given in the procedure for the lab, so I'm not sort of giving you any extra information here. Based on the principles for equilibrium, KSP is going to be your calcium concentration multiplied by your hydroxide concentration squared. Now, remember, with equilibrium expressions, those coefficients tell you about powers. So when you plug in your hydroxide concentration, it's just going to be whatever hydroxide concentration you have. It's not going to be twice that. However, you are going to square the value. Also, when you plug all this into your calculator, make sure you're only squaring the hydroxide concentration. Don't multiply calcium and hydroxide concentrations together and then square the result. You only want to square the hydroxide concentration. Okay, but how do we know the calcium or the hydroxide concentration? And that's where the titration comes in. So, as you know, in a strong acid, strong base reaction, the hydroxide ions from our strong base, calcium hydroxide, will react with the hydronium ions from the strong acid, hydrochloric acid, and those neutralize together to form water. I'm only showing you the net ionic version of this equation. So what can we do with the data we have? And I'll show you where this data will come from in just a little bit. So you'll be provided with the molarity for the hydrochloric acid as part of the data that I'm giving you. And we can use that to figure out initially the number of moles of hydrochloric acid that we have. So to go from molarity to moles, you can just rely on the definition of molarity. And you did a similar thing with the titrations in the lab last week. So you should know how to do that conversion. And remember that hydrochloric acid, being a strong acid, produces hydronium ions in solution, so the number of moles of HCl is the same as the number of moles of hydronium ions, since that's essentially a 100% dissolution. From the moles of hydrochloric acid, we can determine the number of moles of hydroxide ions, which, if you look at the equation above, those react in a 1-to-1 ratio, so that's a pretty simple conversion in that second step. From there, we can determine the hydroxide concentration, which is one of the portions that we need for our KSP expression. Now that's going to be the hydroxide concentration in the initial solution that you filtered. So what you need there is, based on molarity, you need the number of moles, which we just found in the previous step, and we need the volume in liters. And you'll be provided with the equivalence point volumes for the hypothetical titrations, and you can use that combined with the number of moles to find the hydroxide concentration. So that's one piece of the puzzle for KSP. And from that, we can actually find the calcium concentration as well. And the calcium concentration is can be determined from the hydroxide concentration based on how many calcium ions are produced for every hydroxide ion, and that's shown in the top equation above, and a little bit more explicitly in the ice chart. So it's relatively simple to figure out what the calcium concentration is if you know the hydroxide concentration. I'll just put it that way. And I've highlighted those last two in pink because together we can plug those into the formula appropriately and find KSP. Now, you might be asking, what does this all have to do with the values of delta H and delta S? It turns out the equilibrium constant for any equilibrium, including but by no means limited to solubility equilibria, is related to delta G. So if we know our equilibrium constant and we know the temperature, again that should be in Kelvin, we can use the formula that you see here to find the Gibbs free energy change, delta G1. So the formula for that is delta G equals negative R times T times the natural log of the equilibrium constant. T needs to be in Kelvin. R is 8.314 joules per mole Kelvin. And since that has units of joules, you'll want to be sure to convert that into kilojoules, at least by the time you get your value for delta G. Now, if we use the data from the first titration at room temperature and plug in the room temperature in Kelvin for T1, we get the value for delta G for the first temperature titration. So delta G1 there is the Gibbs free energy change for the reaction at room temperature. If we then take our data from the second titration, where we filtered that solution when it was at 100 degrees Celsius, we can plug in that temperature in Kelvin for T2, plug in the titration data to get the K value for the dissolution at 100 degrees. Now remember, a lot of sort of changes don't affect the value of the equilibrium constant, but one change that actually does is changing the temperature. So by changing the temperature, we should expect to get different numerical values for KSP at different temperatures. So KSP in the second equation is not going to be the same as it is in the first equation. R, of course, is a constant, so that stays the same. And plugging all that into the same format of formula, we get delta G2. And once we have delta G1 and delta G2, we can use the formula that I showed you in solving the pre-lab question to find delta H and delta S in exactly the same way that you would do it with the pre-lab, just with different numbers for the temperatures and delta G values. Okay, so before I conclude this video, I just want to show you the data that I'll be distributing to you and specifically show you how to use it. So this is relatively straightforward. It comes in the form of an Excel spreadsheet. So you can see in this Excel spreadsheet we have two trials, trial 1 and trial 2, at two different temperatures. So 25 degrees Celsius is your room temperature titration, 100 degrees Celsius is titrating the solution that was boiled before it was filtered. And for each of these titrations at those two temperatures, you can see that the number of milliliters of calcium hydroxide needed to reach the number of milliliters of calcium hydroxide used in the titration is shown here. So that's the amount of calcium hydroxide used in the titration. So in this example, that's about 6.82 mils for the first trial at 25, 7.06 milliliters for trial 2 at 25 degrees Celsius, and so on. The molarity of hydrochloric acid shouldn't really change. That's always going to be 0.0025 molar. In other words, 0.0025 moles per liter. And in column E here, we have the corresponding volumes of hydrochloric acid solution needed to reach the equivalence point. So these are your equivalence point volumes again in milliliters. Now, there is one thing you need to be really careful with in terms of using this spreadsheet, which is this spreadsheet is actually set to generate some random values for the calcium hydroxide and equivalence point volumes, which means that every time you open this chart, the numbers for those will change. So what you need to do is, when you're ready to start doing this lab, you need to open up the spreadsheet exactly one time and keep it open. And while you have it open, you can scroll down in your lab procedure to your data table and copy the information in this chart into your data table. So you'll actually want to write that in. And again, you want to do that all without closing the spreadsheet, because if you reload the spreadsheet, all the numbers will change and that can mess things up. The numbers here are randomized so that everybody will have different data. You just need to be careful with how you use this. So I think that covers everything that I wanted to cover in this video, so we'll go ahead and wrap it up here. As always, please contact me if you have any questions about how to use any of this. I know the math is kind of involved here, so by all means, please feel free to reach out to me if you're having any trouble using this, or if you're not sure how to answer any of the questions, especially if it is because you didn't actually do the experiment yourself. So we'll go ahead and wrap up here. Hope everybody finds this activity interesting and is able to get something out of it that will help you with the regular lecture class.